Hey there, welcome to another video for Calculus 1. We are going to be doing section 3.3, which is the basic rules of differentiation. I told you all that we would not have to use the limit definition forever, and we're very glad for that. So we're going to go through the rules of differentiation. If you want to see where some of these rules come from, they do come from the limit definition. Your textbook goes through a couple of those. There are some good videos out there for that, but I am not going to spend time on that because that's not the focus of this particular course. I'm going to show you what the rules are. I'm going to give you some examples of how they work. Okay, so we are going to look at first what's known as the constant rule. I do want to show you a little bit of notation here. When you see d dx, that's what's known as an operator. Okay, and so the operator means take my derivative, please. It's very polite. It means take my derivative, please. And so when you see d over dx of 7, that means take the derivative with respect to x of 7. And then when you follow the rule, and the constant rule is the derivative of a constant is 0. Remember, differentiation, derivatives mean change. If it's a constant, it's not changing at all, right? And so the derivative of 7 is 0. So a second way to write that would be if f of x is equal to 7, find f prime. And then f prime of x would be 0. Okay, so this is just kind of a shorthand notation. Another way to think about it is if you did the derivative with respect to x of a function f of x, you would get f prime. So again, this is known as an operator, and an operator, it's just like the limit as x goes to 3 or whatever. It tells you what to do. When you do it, the operator goes away. You've used it up. Okay, so the derivative with respect to x, this d over dx, it goes away when you do the rule. Okay, so I told you a reasoning behind this constant rule. Here's another reason behind it. F of x equals c is just a horizontal line, which means the derivative is equal to 0 because the slope is constantly 0. And that's what our derivative represents, is slope of the line or slope of the tangent line if we have one. And so that's another reason behind it. Okay. All right. So the next rule is called the power rule, and the power rule in section 3 is given just for n being a non-negative integer, but I'm going to extend that because the power rule actually works for any real number n. Okay, so it doesn't just have to be a non-negative integer. That's the easy one to prove, but then you can use some future rules to kind of show that this has to work in general. And I'm just introducing it now because, again, I'm not really giving you the theory behind it. So the power rule says this: the derivative with respect to x of x to the n power is n times x to the n minus 1 power. So whatever the power is as a constant, whatever the number is, you bring it down in front. That becomes your coefficient, and then you subtract 1 from the power. Okay? So the derivative with respect to x of x to the 27th power is 27x to the 26th power. Subtract 1 from the power. That's it. All right. Now, at first, this may not look like it belongs. What's the derivative with respect to x of the square root of x? Well, the square root, we don't have a rule for that. This is power rule, right? But remember algebraically that the square root is actually a power. The square root is the 1/2 power. All your roots can be written as powers, in fact. And so what is the derivative with respect to x of x to the 1/2? It's bring down the 1/2, x, and then subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. And so that's your answer. I do not expect you to simplify. If you did want to simplify, how would you do that? Remember, the negative power becomes a positive power if you move it to the bottom. And then, of course, you could even rewrite it as 1 over 2 square root of x if you went back to that notation. But any of these three I will accept. For most of this chapter, I do not expect you to simplify your derivatives. Should you be able to do it? Absolutely. You're going to need to in chapter 4. But right now I'm trying to focus on the skill of taking the derivative and not as much about the algebraic simplification. My math lab, however, will require simplification. Okay, so just make sure you understand whether you're struggling with the actual derivative rule or whether you're struggling with the simplification process, because that's an algebra thing that you should be able to do from previous experience. I'm happy to work with you for both, obviously. As always, I'm happy to meet with you outside of class time and help you out with any of the stuff you're struggling with, even if it's old stuff like algebra. Okay, just let me know. All right, the next rule, the constant multiple rule. If you have a constant in front of your function, then remember the derivative of a constant by itself is 0 because it's not changing. But if you have a constant times a function, well, think about it. If you were taking the derivative of x squared, you would get 2x according to the power rule. Okay. Well, if that tells you the change of x squared, 2x tells you the change of x squared, then how would 3x squared change? 3x squared would change 3 times as fast, right? So it makes sense that your derivative is just 3 times the change, 2x. And then, of course, I would expect you to combine those and make it 6x, okay? Again, I don't really care about overly simplifying things from algebraic standpoints, but multiply 2 constant together, yes, I expect that. So, all right, so how do we do this? So the derivative of 17x cubed, the 17 just kind of hangs out. And we take the derivative of x cubed and you get 3x squared. And then again, I would expect you to put that together and give me 51x squared. And certainly I would be fine with you jumping right down here. I think you can do 3 times 17 on your calculator or in your head and skip this middle step. But I just want to show you where it comes from. Okay? So we take those two and we put them together with the sum rule. And the sum rule is actually the sum or difference rule, plus or minus. Right? So if you want to take the derivative of 2 things added together, you just take the derivative of each piece. So if I want to take the derivative of x squared plus 8x, I take the derivative of x squared, and then I take the derivative of 8x, and then I add those together. What's the derivative of x squared? 2x. Bring the 2 down, subtract 1, get a 1. What's the derivative of 8x? We haven't really talked about it. This is still a power, right? This is power of 1. So the 1 comes down in front, so 1 times 8 is 8. And then I get x to the 0 power, which is actually just a 1. Another way to think about that is that 8x, y equals 8x is a straight line with a slope of 8 constantly. And so if the derivative means slope of the tangent line and it's a straight line, the tangent line is the line and the slope is 8. But either way, the derivative of a constant times x is just a constant. So here's the derivative of the function x squared plus 8x. All right, I want you guys to try one here. You go ahead and try taking the derivative of a polynomial. Let's say x to the 4th minus 7x squared plus 11. You guys go ahead and pause the video now and try that one and see what you get. Okay, so the derivative of x to the 4th, bring the 4 down, subtract 1 from the power. The minus sign stays, so you get minus 7 times 2 is 14x to the 1st power, and then plus nothing. The derivative of 11 is 0, so you get 4x cubed minus 14x. Again, that's the derivative function for this function here. Okay, right now, don't worry as much. Yes, it's for the tangent line and all that kind of stuff, but don't worry as much about that right now. Just focus on the rules. Okay. Now, I do want to show you a little bit about where one of our rules comes from. Okay, and that's the rule for e to the x. If you have the graph of y equals e to the x, y equals e to the x is the unique curve, exponential curve anyway, where its slope of its tangent line at a y value of 1 is equal to 1. And it turns out that that's actually true for all of the points on e to the x, that whatever the y value is, the slope is the same at that value. Okay, and so what does that mean? Well, it means a couple of things. The first thing it means is that e, this number, is a unique number. Just like pi, it's irrational, so you can't write it all the way out. These are the first few digits. But it's the unique number that satisfies this exponential limit. And because it satisfies this limit, then the derivative of e to the x turns out to be itself e to the x. Okay, so that's your next rule, that the derivative of e to the x is e to the x. And so what I'd like you to do is I would like you to pause the video and try this derivative here, all of this stuff. I want you to do that derivative. Okay, you've got a cube root in there. You got to handle that differently, whatever. So I want you to try this derivative, pause the video, and then we'll talk about it. Okay? Okay, so how do we do the derivative of each piece here? That's right, it's a sum difference, so we do the derivative of each piece. 11x to the fifth, bring down the 5, 55, 5 times 11, x to the fourth, subtract 1 from the power. I can't do the derivative here like it is. I can't do the derivative of the cube root, so I've got to do the derivative of what? I'm going to do the derivative of x to the 1/3 power this time. Cube root is 1/3 power, square root's 1/2 power. Okay, we'll do that in a minute. Minus 8 e to the x. What's the derivative of e to the x? Is e to the x. The 8 just comes along, so you get 8 e to the x. And then, do I do the same thing with square root of 7 as I did with cube root of x? Actually, no, I don't, because this is not a variable. It's a constant. If 7 is a constant, the square root of 7 is also a constant, and so it is a derivative of 0. So let's rewrite these. 55x to the fourth, and then plus the derivative of x to the 1/3, bring the 1/3 down, x, subtract 1. 1/3 minus 1 is negative 2/3, minus 8 e to the x, and again, I'm fine with you leaving it with a negative exponent and whatever. So the derivative of this 4-term expression is this 3-term expression. That's the derivative. Okay? So don't forget, I did say don't worry about it right now, but don't forget about the fact that the derivative tells you, right, it tells you the slope of your tangent line. And so for the graph of y equals 2x minus 1/2 e to the x, for example, if I wanted to know what the value of the slope at the tangent line was when x is equal to 0, then I would need to take this derivative. I would find y prime, that's another way to write it, right? Y prime or dy dx. What's the derivative of 2x? 2. What's the derivative of 1/2 e to the x? It's also 1/2 e to the x. And so if you want to find the slope of this tangent line when x equals 0, you plug in x equals 0. And so you get 2 minus 1/2 e to the 0. E to the 0 is 1. And so the slope of the tangent line is 2 minus 1/2, which is 3/2. And so the slope of that line right there is 3/2. Okay. For this line, what they did is they want to know the horizontal tangent line. Well, horizontal means slope equals 0. And so they take the slope given by this formula and they set it equal to 0. 2 minus 1/2 e to the x. Well, I'm going to take 1/2 e to the x to the other side. Multiply both sides by 2. And then if I want to solve this for x, I have to take the natural log of both sides and get natural log of 4. And I can plug that into my calculator to get an approximate x value of 1.39. And so what does that mean? That is the place where the slope is equal to 0, where this function has a horizontal tangent line, right? So if you watched the video on the conceptual idea of derivative, the one that I didn't create but that I posted for you, they talk some about the tangent line. So this is just a reiteration of what we're talking about with regards to the tangent line and how it works. Okay, so don't forget about that. Again, we're not going to focus on that right now, but I just want that in the back of your head while you're doing all these derivative rules that, hey, we're finding a formula for the slope of the tangent line, for the instantaneous rate of change, and it means lots of other things that we'll talk about later. One last thing, and I want you to do this problem. So the derivative is how f is changing. Well, it's possible to take the derivative of the derivative function. And so we call that the second derivative. And the second derivative tells you how the first derivative is changing. How do you find the second derivative? You take the derivative of the first derivative. So it is a step-by-step process. There is no way for you to get smoothly from f to f double prime to the second derivative. There's no way to do it. The first thing you have to do is find f prime, and then you can take the derivative of that function. Okay? So I want you to try that, noting that this is 4 over x squared. We can't do a fraction right now. We can't do it. So you need to rewrite this. Remember how we rewrote square root earlier? There's a way to algebraically rewrite this part of the f of x function also so that you can use just the plain old power rule. Okay, so rewrite f of x first, and then take the first derivative, and then take the second. Okay, pause the video and come back and we'll check it out. Okay, so how are we going to rewrite f of x? F of x is going to be rewritten as 10x cubed plus 4x to the minus 2. Remember, I showed you a negative exponent earlier in this video. I went the other direction, but I was hoping you would catch on to that. So this is f of x. If you didn't have this for your function, you may want to pause the video again and try to find f prime and f double prime. So let's take a look at those. F prime of x, bring the 3 down times 10, you get 30x, and then subtract 1 from the power. 3 minus 2, 1 is 2. 3 minus 1 is 2, so you get 30x squared. 4 times negative 2 is negative 8. And then if I subtract 1 from negative 2, that becomes negative 3, right? Remember, if you subtract negatives, you add the numbers together, so you get negative 3. Minus 9x, the derivative of 9x is just 9. And then the derivative of the constant is 0. So your first derivative is 30x squared minus 8x to the negative 3 minus 9. To find the second derivative, we take the derivative of this guy. Same rules apply. Doesn't matter what you call it. Same rules apply. So bring the 2 down. 2 times 30 is 60x to the first power. Negative 8 times negative 3 is positive 24x to the negative 4 power. And then again I have a constant. The derivative of negative 9 is 0. And so this function right here, this function is the derivative of f prime. But it's the second derivative. This notation represents that it's the second derivative of this original f. All right, and you can keep going. You can take a third derivative, a fourth derivative, and they all have meaning and value. We will focus on the first and second derivative in chapter 4. And for those of you in engineering, you guys would end up working on the third and fourth derivatives even sometimes. But for us, we'll focus on the first and second derivative, but we probably won't do very much with that until chapter 4. Okay, so there's a 3.3 worksheet. It actually includes 3.3 and 3.4 together. So watch both of these videos, 3.3 and 3.4 together, and then go and do the practice problems, okay? All right, we'll see you later. Thanks.